So good afternoon, everyone. Welcome to the second to last Heidelberg Joint Astronomy Colloquium of this calendar year. It is an honor and a great pleasure to introduce Nate Bastian from Liverpool John Moores University. Nate is a world-leading expert on stellar populations, star clusters, globular clusters, and in particular, the problem of multiple populations in globular clusters. And particularly, I would like to highlight his annual review on this topic from 2018. Nate started his career at Utrecht University, where he received his PhD in 2005, working with Henny Lamers. He moved on to UCL in London, where he held an STFC postdoctoral research fellowship. After that, he received the Ernest Rutherford Fellowship, which he held in Cambridge and Exeter, spent a couple of years in Munich, and then moved on a Royal Society University Research Fellowship to LJMU, where he is today, and has been leading a group called Multipops on an ERC consolidator grant, among others. And today, Nate is going to talk about to us about the origin of multiple populations within stellar clusters, an unsolved problem. Nate, the floor is all yours. And before you start, I'd like to honor our tradition here for everybody to unmute and give our speaker a very, very warm welcome. Go ahead.
Great. Well, thank you very much for that very nice introduction. So today, as Dietrich said, I'd like to talk about the origin of multiple populations within stellar clusters. And I will argue that this is probably the most interesting problem in astrophysics that you may not have heard of. And so my hope today is to get everyone excited about this problem. This is a really unsolved problem where, just to give the conclusions away, we really don't know where this is coming from. And we really need new people with new ideas to try to help us get a handle on where this is coming from. And so I'll be talking about a lot of work that we've been doing in Liverpool and elsewhere over the past few years with this great group of people highlighted here and a few others as well. And so just as a way of introduction, when you look at your favorite galaxy in the night sky, what you see is that there's a whole bunch of little blurry marks on these images that get in the way if you're actually trying to study the galaxy underneath. And so for example, this is one here. Now, it turns out that the vast majority of these objects in this image are not foreground stars or background galaxies. These are in fact globular clusters that are associated with this galaxy. And we know that virtually every major galaxy in the universe has a population of globular clusters that assembled with its host galaxy. And if we had infinite resolution, which we can cheat by using the Hubble Space Telescope for globular clusters in our galaxy, what we would see if we could zoom in on each one of these globular clusters is this. They are dense collections of stars, hundreds of thousands or even millions of stars held together by their own gravity of just a few parsecs across. So they're extremely dense stellar systems. And again, if we had infinite resolution, we could then get a CMB of every star within this cluster. And this has been done now for the last 80 or 90 years. And what we've learned, at least for globular clusters in the Milky Way, is that they're all old. There could be an age spread, but they're all older than, say, about, or at least the vast majority are older than about 10 gig years or so. And while there's a metallicity distribution amongst the globular clusters, at least compared to the solar metallicity, they're all extremely metal poor. And people have been studying for globular clusters for a long time now. And they're some of the oldest luminous objects that are known in the universe. We know it because they are found around all major galaxies, and actually the cluster populations are linked to the galaxy properties themselves. They must be intimately linked with galaxy assembly. And therefore, as quoted by William Herschel back in 1814, globular clusters are undoubtedly the most interesting objects in the heavens. And the more you study globular clusters, the more fascinated you become with them. And so there's been a long history of studying globular clusters, or actually using them as tools. They've been used to determine the structure of the Milky Way, going back to the 1910s debate. They've been used to understand and calibrate stellar evolution and stellar population models. They've been used to constrain the formation and evolution of the Milky Way, as well as other nearby galaxies. And they've also been used to find and study stellar exotica. And what I mean by that is stars like low mass X-ray binaries that have a much higher prevalence within globular clusters than they do in the field. And therefore, it's a type globular clusters, the dense environment opens up specific routes for stellar evolution that are just not possible in the field. Now, if we go back to what we learned in kind of our Astronomy 101 course, we are taught that there's two types of stellar clusters. There's open clusters and globular clusters, where open clusters are low mass, low density systems. They have a few members to maybe 10 to the 4, 10,000 solar masses or so. They're young from forming today to the oldest ones are a few gig years old. They belong to the disk of the Milky Way. And because of that and their youth is that they're all around solar metallicity or so. And you can contrast that with globular clusters shown here in image of M80. These are high mass, high density systems of tens of thousands up to millions of members. They're all old, as I mentioned before. They're low metallicity, and they belong to the bulge and halo of our galaxy. Now, so we know that globular clusters and open clusters, at least traditionally, are put into different groups, but they had some common characteristics, and they were thought, both of them were thought to be simple stellar populations. And what that means that it was thought that all stars have the same age, at least with some very small tolerance, so the age spread within a cluster is likely to be less than 1 or 2 million years. It was thought that all stars are going to have the same abundances, modulo some stellar evolutionary effects. So you have a range of stellar masses and stellar rotation rates, and therefore they were the perfect case to use it to study stellar evolution. So every time somebody developed new stellar models, a new stellar population model, the first thing you would do is you go to and you compare that with what you expect from observations of your clusters, see how well your models are doing. Now, because globular clusters were these unique, very dense systems that seem to be different from open clusters in some way, it was thought that globular clusters could only form in the special conditions of the early universe. And that was a prevailing thought, at least until the 90s, if not later. And in the last couple of decades, we've had some big surprises when it comes to globular cluster research. So the first surprise is shown here. If we go back to our favorite Mach diagram here. So this is a CMD actually of a Milky Way globular cluster, NGC 2808. This is a CMD made with HST with a wide field planetary camera 2. It's kind of the best you could do up until the early 2000s. And this looks like a traditional simple stellar population, where you have just one unique stellar population, main sequence, turn off, red giant branch, etc. However, with the advent of the advanced camera for surveys in HST, we could zoom in onto the main sequence in unprecedented precision to really see what was going in there. And when they did that for 2808, what you see is it wasn't a single population. It wasn't just a single main sequence, which is what we would have thought. In fact, this cluster has 3 distinct main sequences within it. And if you do the fitting, is that the only way you can explain this is actually by different helium abundances, which is unheard of in stellar population works up until this data was taken. Now, the second surprise came just actually a few years before. Again, it was opened up with the advent of the Hubble Space Telescope. So what I'm showing here, this is an image of Omega Centauri. This is the most massive globular cluster in the Milky Way. It's a few million solar masses. It's aged about 12 gig years old or so. And if we we look at near starburst galaxies, this is an example of the antennae starburst galaxies. These are 2 spiral galaxies that are colliding with a huge burst of star formation. You can see where recent stars are forming, shown as pink here, H alpha. And you zoom in on one of these knots, star forming knots, what you find is that you find a globular cluster also of a few sub-million solar masses, but now it's extremely young. In this case, it's only about 7 million years old or so. And in fact, its radius is even slightly less than that of Omega Cen. So this is actually a cluster that's forming recently as a higher density, similar mass and higher density of the most massive cluster in the Milky Way. So these things, and this is just one example. There are in fact thousands of these examples within this one single system of the antennae. And therefore we can say is that they have the similar masses and densities of globular clusters. This is exactly what we'd expect for what to view globular clusters when they were forming in early epochs of the universe. Therefore, we can say is globular clusters are in fact still forming in the local universe today. So we can use objects like this, shown here, to actually understand how objects like this formed, even though that formed at high redshift. Now, this is just a few more examples of where we can find these young massive clusters or young globular clusters. This is NGC 34 and NGC 7252. If we zoom in with HST again, these are two nearby recent mergers. There's this object here is 100 million years old, and it's 10 to the 7 solar masses. And the current record holder, in fact, is this guy up here. It's W3 in NGC 7252, with its age is about 500 million years, and its mass is 10 to the 8 solar masses. So this is the most massive cluster that's known in the universe. And in fact, this mass comes from a dynamical mass. We actually can measure the virial mass of this cluster because it's semi-resolved with HST, and we can also get high resolution spectroscopy. And if you don't like that one, well, the next most massive one in this galaxy is a few times 10 to the 7. It's also the same age. And if you don't like that one, this one's also about 10 to the 7. So we have a whole mass function of clusters in this galaxy that formed during this merger. All of them, or at least the ones that are visible in this image, all of them are more massive than the most massive globular clusters in the Milky Way. And you don't need to go to these kind of extreme environments. This is an image of NGC 1705. This is a nearby blue compact dwarf galaxy. It's only 3 or 4 megaparsecs away. And near the center, but not quite the center, it had a recent starburst. It formed a 10 to the 6 solar mass cluster about 15 million years ago. And this is just a regular kind of puny low mass spiral. So these things can still form globular cluster-like objects as well. So if we go back to multiple populations, one of the main takeaways of this talk is that globular clusters are not simple stellar populations, that every globular cluster in the Milky Way that's been studied to date shows these anomalies. And what that means is if you observe them in the correct HST filters, especially in the ultraviolet, you start seeing spreads and splits pretty much in every evolutionary phase. So red giant to the horizontal branch, and then even the main sequences. So this is another one where on the main sequence, you can work out multiple distinct main sequences. Similarly, if you go and you observe individual stars, you measure their abundances, we now know that the stars do not all have the same abundances within the clusters. We see distinct abundance trends. So if, for example, iron remains constant amongst all the stars, but things like sodium and oxygen are found to vary on a star-by-star basis. Not in any random way. We start seeing abundance trends like this, where in sodium and oxygen are anti-correlation. That's going to be a clue to what may be driving this phenomenon. As I mentioned, all globular clusters studied to date show these anomalies, but interestingly, they all differ in the details. So in fact, you can use these kind of CMDs to provide a fingerprint of each globular cluster within the Milky Way. Each one is slightly different in the details. So if we come back to our the most extreme case in the Milky Way, NGC 2808, this is one that, again, as I say, you have to have different helium abundances. What you're talking about here is a huge helium spread. Nominal would be 0.25. In mass fraction, that would be this main sequence here. And the only other way to explain these populations here is by adjusting helium to rather extreme values of mass fractions up to 40%. And that's really unheard of in stellar populations, at least for unevolved stars. These are not due to age or metallicity differences. In this particular case, these spreads can only be explained by helium abundances. What we see here, but also every cluster we look at, is that the so-called second generation or the anomalous stars are in fact the majority of stars. 60% of the stars in this cluster would be helium enriched, only 40% would be considered normal or somewhat normal. So what is causing these strange color magnitude diagram features is the fact this is, if you look in the UV, these are spreads in carbon, nitrogen, and oxygen, that these atoms form molecules that have very, very deep molecular features in the UV. You actually see high precision photometry. So if you see UV colors that are varying, you know that it's basically nitrogen for the vast majority of this. So that's what's causing this. And if you look in optical colors, there are almost no molecular bands strong enough to see. What we're seeing here is differences in effective temperatures, which in fact is driven by helium differences. But it's one thing I want to emphasize that I always get asked at the end of every talk, well, could these be age differences? And the answer is no. Age is not a driving factor. In fact, all globular clusters have coeval populations with the measurement uncertainties, where the best you can do at old ages is about plus or minus 300 million years. So they're coeval within 300 million years. And I'll come back to that at the last part of the talk to say how we can do better recently and constrain that by more than a factor of 10. Another interesting idea behind this phenomenon is that stars somehow in globular clusters know about where they form. So if we go back to our sodium and oxygen plot of every point here is a star in 47 Tuc, a massive globular cluster in the Milky Way, is that we see this sodium oxygen anti-correlation. And in this cluster, we see is about 60% of the stars are going to be anomalous, and only 40% would be considered normal. And if you compare that to the halo stars, stars at the same metallicity range in the bulge of the halo, what we find is about 97% of halo stars would be down in this diagram, part of the diagram here, and only 3% would be up in this diagram here. So there's really something unique about globular clusters that is somehow altering the chemistry of the stars within them. We don't know if it happens at formation or if it's evolution after the fact. Another piece of the puzzle was put by Antonino Malone and collaborators with a large HST survey that came out a few years ago, is that we see that the types, the strangeness, if you will, of the chemical anomalies seen in globular clusters depends on the cluster properties. So more massive clusters have a higher fraction of the stars that are so-called enriched, so-called strange. So these would be sodium enhanced, helium enhanced, nitrogen enhanced. So these clusters up here, which would include 2808, 47 Tuc, and Omega Cen, they have a very large fraction of their stars are anomalous. So anomalous meaning they're not found in the field, and low mass clusters are down here. So they might have 50-50 or so of their stars being strange to normal. But it goes beyond that. Not only do higher mass clusters have higher fractions of strange stars, is that the strangeness of the stars also correlates with mass. What I mean by that, if you actually look at the total run of nitrogen spread or sodium spread or helium spread, take your favorite element that spreads in a cluster, higher mass clusters, not only do they have a higher fraction of stars that are anomalous, the actual spread that you observe them is also larger. So 2808 has a larger spread than lower mass clusters. And so this is very hard to explain because, of course, in order to get the material that you might need to form multiple generations that are nitrogen enhanced, you need more of that in order to form more of the stars. But on top of that, you need to put that into a larger spread. And that is going to be a big problem for a lot of the scenarios, as we'll see throughout this talk. So what are the observables of this phenomenon, the multiple populations phenomenon? So we see correlations and anti-correlations. So sodium and oxygen are anti-correlated, nitrogen and carbon are anti-correlated. We see large spreads in aluminum, but other elements show little or no spread. So like magnesium, iron, or other peak elements. Calcium do not show any spreads. We see discrete main sequences and turn-off subgiant branches. Basically every part of the CMD, including unevolved stars, shows these anomalies. They're found in red metal-rich and blue metal-poor clusters. So this is not a metallicity effect. We see the same spreads independent of metallicity. And therefore, what you can see is that the elements that are seen to vary are known to be in hot hydrogen burning. And so only certain stars can produce the right abundances. And the first thing to note here is supernova. No type of supernova known can provide anything like the chemical abundances seen. So you'd always get some spread in iron or calcium or things like this, or you get different anti or correlations. So the types of stars that have been suggested are AGB stars, so which are evolved 3 to 8 solar mass stars, although they actually give the wrong sodium oxygen anticorrelation. That's kind of a detail I'll put aside. They're the ones that people have been investigating the most over the past 2 decades. You have rapidly rotating high mass stars or interacting massive binaries, or recently people have even tried to come up with extremely massive stars. And by that, I mean stars more massive than 5,000 solar mass or so. And that should tell you we hit some dead end, that people are really kind of scraping the bottom of the bucket into crazy ideas because we really don't know where to look. And so, as I say, we're going to need some new ideas to really push this forward. So what kind of ideas have people put forward? So I'm going to take you through the most popular one, which is the AGB scenario. But the other scenarios put forward are basically the same, although the timescales may vary different a little bit, and the types of stars are going to differ. So the basic idea is that t = 0, you form your first generation of stars. This would be a single simple stellar population that we know and love in open clusters, or that we would typically imagine how globular clusters form. And that's shown here. After 30 million years, the most massive stars that are going to become AGB stars begin to evolve. They shed their material. So AGB stars produce a lot of polluted material as they're mixed, hot bottom burning within them. So they can dredge up material that's been nuclearly processed. And those winds are going to cool, and they're going to collect in the center of the cluster. So you're going to end up with a reservoir of gas there. However, in order to get the abundances right, you can't just form stars from that material. You need to accrete then a lot of pristine gas from the surroundings. What I mean by pristine is not zero metallicity, but the exact same abundances that formed this generation up here. And so why a gas cloud would be sitting next to the cluster not doing anything and would have to be accreted at just the right time, that's kind of left as an exercise to the reader. No one really knows, but that's just a necessity in order to explain what the models need in order to come anywhere near the observations. So once that happens, you can then form the second generation of stars, and the second generation is going to be more centrally concentrated. They're going to be forming in the center of this gas cloud. And then these are the stars that are going to have the strange abundance patterns. But as I mentioned, these stars are the majority of clusters, of the stars in clusters. So in order to get even anywhere near the right observations, in fact, you then have to lose the vast majority of the first generation stars. In fact, 95% or more of these stars have to be lost. Again, there's no physical mechanism that's been really put forward that would explain why these stars would be lost after they've been in place for at least 30 million years. So again, it's just kind of left up to an exercise, but that's just to the reader, but that is just what is required for the models. And so it's been kind of multiple epicycles have been put into these models to then get closer and closer to the actual observations. So this AGB scenario, as I say, it's been the most favored in the literature. It makes some certain predictions that we can actually go out and test. And that's how I got involved in the study, by using young massive clusters to actually test this scenario. So it makes some predictions. The first is that the second generation is going to be more centrally concentrated than the first. And that's largely true, although there are some complications. It's not true for all clusters, but for the majority of clusters, that is true. So I think that's okay. So in order to have enough material to form the second generation, globular clusters must have been 10 to 100 times more massive than presently seen. This is known as the mass budget problem. This is why clusters need to lose 95% of their first generation stars. This is directly contradicted by observations of stars in dwarf galaxies done by Soren Larsen and collaborators. And we've also been looking at this, the actual globular cluster population properties is directly contradicted of this. This scenario needs clusters to retain stellar ejecta and accreted gas for long periods of time in order to use that material to form a second generation of stars. And therefore, if you're forming multiple generations of stars, then you should show an age spread within, or multiple bursts within your cluster. So we should be able to look for these young globular clusters, these massive clusters, and they should be forming multiple epochs of stars within them. And that's something relatively easy that we can look for. So let's look if we see that. So if we go back to our favorite galaxy merger, this is the antennae. What I highlight here in circles is a cluster population that we went out a long time ago and got a bunch of optical spectra. And we combine that with 130 other spectra from the literature. And then this is just some of the images of the clusters within the galaxy from HST. And these are the spectra that we got. And what we're looking for in these spectra is absorption line spectra that might have emission lines superimposed in order to have evidence of a second generation of stars forming. So H alpha, oxygen 3, H beta, things like that. As I mentioned, we did this for 130 massive clusters, both from our samples and those from the literature. They're shown here as their age versus their mass. I highlight here, this is the mass of a typical globular cluster in the Milky Way. So you can see they're about similar mass, but they go all the way up again to 10 to the 8 solar masses. This is the range of which the AGB scenario would expect the second generation to be forming. In 130 clusters, we found no evidence of ongoing star formation in any of the detected clusters. Therefore, the observations here that we presented here ruled out continuous duration star formation within them and disfavored discrete bursts. And after we published this, we realized we could do better. So in fact, we could put even tighter constraints on multiple epochs of star formation within these massive clusters. And we're going to focus on these clusters up here, these very, very massive clusters, and use them that their potential well should be enough. They're much more massive than even the most ancient globular clusters known. So if this process is happening, it should be happening in there. So to do that, we're going to use the same techniques that people have done For galaxies, we're going to do our stellar population fitting. So we got an integrated spectrum, a very high sinusoidal spectrum of this cluster, and we fit multiple stellar populations to it. And we asked the question, what is the star formation history of this cluster based on its integrated spectrum? This is what's been done for galaxies for a long time. And so we just applied the same technique to this cluster. And to at least not our surprise, it was found to be a single population of 100 million years, 2 times 10 to the 7 solar masses. So this was one of the most massive clusters known. It's a single stellar population. There was no evidence for any secondary star formation within them, down to just a few percent we could put on this. And this was in direct conflict with the predictions of the AGB scenario. And so this is just one of the many clusters, studies that we've done using these young massive clusters to constrain scenarios for multiple populations. What we've seen is that these very massive clusters are gas-free from very young ages, less than 3 million years. And this is a problem for massive star scenarios that have been put forward that need them to retain their gas for tens of millions of years. There's no evidence for ongoing star formation in any young massive cluster studied to date, older than about 10 million years or so. And that's also shown in integrated spectroscopy, where we didn't find any evidence for multiple bursts or extended star formation histories. We've looked with ALMA, extremely deep ALMA observations. We've never found any gas. We've looked with HST to look for dust within these massive clusters. Never found any dust. It turns out that young clusters are extremely efficient in getting rid of any gas and dust within them that's left over from star formation, and they're never able to accrete gas from their surroundings. And we think this is just due to stellar feedback within them. Therefore, models with multiple star formation events are disfavored by observations of young massive clusters. And the conclusion of this section of the talk is that previous popular models do not agree with observations of young massive clusters. And so the question that we reached a few years ago is, okay, but then how do we make progress on this? Where do we look to try to get new evidence for what's going on within these clusters? And then we asked the question very simply, are multiple populations restricted to the old globular clusters? And putting it another way, are young massive clusters and globular clusters really the same thing, or are they fundamentally different beasts? And this was all initiated at a meeting that we had in 2014 in Sexton, where one of the new ideas coming out at the time was that maybe globular clusters really were unique, is that there was some kind of cosmological formation mechanism that only at high redshift, say above redshift 5, that could form globular clusters, and therefore we should be looking for that same type of strange physics in order to explain the multiple population phenomenon. And so in order to address that, what we started to do is we realized that in some of our nearest galactic neighbors, the Magellanic Clouds, is that they do have massive clusters, so young clusters, or clusters in fact of any age from forming today, all the way up to the ancient globular clusters, so 12 gig years or so, at all ages, that are all globular cluster-like masses. So we tried to find, I think it was 18 clusters in the end, that all have about the same mass, about 10 to the 5 solar masses. So we're trying to remove mass as a limiting factor, but a large range of ages, and ask the question, do they have, where do we find multiple populations, these chemical anomalies, and where do we not? Then we also then did VLT ground-based spectroscopy surveys for nitrogen, carbon, and oxygen directly. And then recently we've been going into MUSE, trying to use the kind of most state-of-the-art instrumentation to look for sodium variations. And this is also their HST program, where we use the special filter, is kind of discovered by Soren Larsen, who realized that there was this F343N filter, or narrow U, that sat right onto this line here, which is an NH line, a molecular nitrogen line. So when nitrogen is overabundant, you get a very, very deep line. And so this is the ratio, I should say, this is the ratio of 2 stars, one with a normal abundance, one with an enriched abundance that you see in globular clusters. And so this filter is kind of perfect for picking up these variations. And then we've published the results in, I was amused to see when I actually collected this in a very large numbers of papers over the past few years. So this is the references here. And I'll just try to summarize the highlights of this survey that's been going on since 2017, 2016 or so. So this is our sample, our HST sample anyway, the Magellanic Clouds HST multiple population survey. So here I'm showing age of the clusters in gig years, mass, on the y-axis here. Again, to draw your eye, this is the typical mass of a globular cluster, an ancient globular cluster, shown here by 10 to the 5 solar masses. So you can see we've all tried to stick around that mass. The yellow points were the original survey. Based on that, we had a follow-up survey which added some blue points. So I'll explain why that's there. And the answer is that when you plot things logarithmically, they look very different than when you plot things linearly. And so we discovered something that we never would have expected based on logarithmic plots, which I'll come to in a second. And then we added this guy up here. This is an ancient cluster, NGC 121 in the SMC. This is the only kind of classical globular cluster in the SMC. And we added that guy, not because we were wondering if it would have multiple populations really, but if we didn't find multiple populations there, then no one would believe the rest of what we said, because this is a classical globular cluster in every way. And so that was just to validate our survey strategy. And what we found is that yes, we did find multiple populations there. So that was no surprise. So then I'll take you through the story as how the data came in and the surprises that we found. The next data that we got was for these 4 guys here. And the first one was Lindsay 1. So this is a massive cluster in the SMC studied by Glatt and collaborators, which was when it came to my attention back in 2008 or so. It's a massive cluster, a few times 10 to the 5 solar masses, 7.5 gig years. Therefore, its formation was about redshift 1. If we're keeping in mind that we're thinking maybe a cosmological effect could be here. And when you see this is a combination of HST colors, and you can see is that the RGB is in fact split within this cluster. If you take a cut across this, you make a histogram, you see it's multimodal. We went out with VLT spectroscopy, and you can see, in fact, we found a nitrogen spread within this cluster. So this is a very clear case where we found multiple populations, both photometric evidence and spectroscopic evidence, a very clear case. So if we go back here, just to cut that short, we found them in all of them. And this is when we started getting excited because 1, this rules out any kind of cosmological effect, at least going down to about redshift of 0.5 or so, is that this was a very common phenomenon. And then I got very confident saying, well, surely then we're going to find it everywhere. So it's either in all massive clusters or just the ancient globular clusters. So the next ones we looked at down here was this kind of high mass cluster there, NGC 419 in the SMC. So 1.5 gig years, again, very massive, 2 times 10 to the 5 solar masses. And if you look here, then this is the strange color combination with HST. This is the kind of spread that we are expecting based on our models. And then we didn't find any spread here whatsoever. So this was a case where we did not find multiple populations within the clusters, and that was quite baffling. And so if we can skip to the end, we didn't find multiple populations in any of these clusters. And so what is going on there? During the meantime, Carmela Lardo and Ivan Cabrera-Ziri developed a technique to use integrated spectroscopy to look for multiple populations in extremely massive young clusters, ages 30, 50 million years old. And they did not find any evidence of multiple populations in these kind of clusters. This is the most massive and old open cluster that had been looked for multiple populations in detail, Berkeley 39. It did not find multiple populations. And then we found this one, NGC 1978. It's a massive cluster, 2 gig years old or so. It did have multiple populations. So this was a bit. Then when we got our additional data, additional increase of the survey, this is what we got as well. These clusters all did, and then this cluster down here did not. So we're starting to build up a very unexpected and unique picture of where and when multiple populations can be found within stellar clusters. And then also we recently expanded the technique to look for multiple populations in integrated light with very massive clusters. And we found evidence in some galaxy interactions, 10 to the 7 solar masses or so. We did find it at 3 gig years, but then did not at 500 million years. So this seems to be an age limit of when we see multiple populations coming in or not, which was totally unexpected. Now, one of the great things we can do with NGC 1978, and I think that over the next few years, it will be recognized that this cluster is going to be the Rosetta Stone for the multiple populations and actually understanding globular cluster formation and evolution, is we can start looking for age differences between the different populations. As I said, this is a cluster that does have multiple populations. In ancient clusters, the best you could do is say that the 2 populations within them are coeval to within 300 million years. But because this cluster is so much younger, we can actually do much better. In fact, we can get errors down below 20 million years old, 20 million years or so. And to do that, what we recognized was that in the optical, there's no effect of multiple populations in these bands. But in the UV, there is. So we could, but in the subgiant branch here, this is in the optical, this is extremely sensitive to age. So if there's a slight difference, even 10 or 20 million years old between the two populations, we should see one lying on top or below the other one. And we can separate them using UV colors. And when we did that, and then go back to the optical, look if they are coeval or not, we found in this cluster, the age difference was 1 plus or minus 20 million years. And to keep in mind, in order for the AGB scenario to work, they needed to be age difference of at least 30 million years. We can already rule that out with high confidence. We've recently been able to expand this and do this for a second cluster with very similar techniques. And you see 2121 was survey. Chino found that the age difference was 6 plus or minus 12. So again, they're coeval in two cases where we can rule out any age differences, any significant age difference between the two populations. One of the other unexpected trends that we found here is if we plot the age of our sample versus basically the width of the RGB, which is a proxy for nitrogen spreads within the clusters, we start seeing this correlation, or at least some of us see this correlation. And we note that all of these are upper limits. In fact, this is where it's very tough. We're starting to hit the error bars. So these are all non-detections. We start seeing some correlation here, and they're color coded as a function of mass. So what might be driving this? Again, this was totally unexpected, but it stands that we only see this effect for clusters older than 2 gig years. We don't see it for younger. That the only idea I have, because I don't know how to explain this, is that as we look at older clusters, we're always looking at the RGB. So we're looking at decreasing stellar mass in the RGB. And stars that are older, that are on the RGB, that are older than about 2 gig years, these all have masses below 1.5 solar masses. All the RGB stars in these clusters are above 1.5 solar masses. And maybe that's one of the clues that we can use to go forward, or maybe that's a red herring and it's not actually related to the problem. So if this limit is 1.5 solar masses, one idea that I have that could be quite exciting is that there is a stellar structure change at stars within this range. Stars with masses above 1.5 solar masses can continue to be rapid rotators throughout their main sequence, and main sequence turn off lifetimes, where stars below this get magnetic fields, they get magnetically braked, and they're slowed down over the course of their, over the hundreds of millions of years that they're alive. Now, there's no reason why magnetic fields should create multiple populations. So this is just more of an empirical idea that stars, it's only in low mass stars where we see this phenomenon, that we don't see it in these higher mass stars. And maybe that difference is related to stellar rotation. Which raises the really exciting question then is, if we look at some of these young clusters here, can we find multiple populations on the main sequence? Can we really nail this effect that's a stellar mass issue, that if it was, then stars that were just slightly younger than these stars, the stars in this cluster, they should show multiple populations. So we convinced the HST TAC to give us a ton of time to try to go super deep down the main sequence of this cluster, NGC 419. And what we found out is, unfortunately, it's very difficult. And the reason is we're going to very, very faint magnitudes. And this is the type of spreads that we are expecting to see. So spreads of about 0.1 in color or less down at 25th magnitude in the ultraviolet. And that turns out to be extremely difficult to do. So the result by Ivan and collaborators earlier this year was that it's inconclusive. We could rule out extreme spreads, so spreads that might be there in, say, 47 Tuc or 2808, or these kind of massive extreme clusters in the Milky Way. But more normal clusters, it just was lost in the data. And the exciting thing is we got, based on this, we got new observations approved that should be taken in January, where we should be able to go a magnitude deeper. So the exposure times are subsequently longer. And so hopefully next time I speak with you, we'll have the answer. And I expect that we're going to find multiple populations on the main sequence. But as I say, it's a very, very difficult measurement to make. And so where we've been pushing recently is trying to leverage HST with MUSE. And this was an idea that the MUSE GC GTO team had to look at, again, an extreme globular cluster like 2808 in the Milky Way. This is an ancient globular cluster. This is HST filters. So you look at basically a color diagram in some special combination of filters. What you see is that you see very clear these different populations coming out. And what they did was say, okay, well, if you select the stars based on HST, and then combine all of their spectra together and analyze them like you would one star, we can then start doing detailed chemical abundance differential analyses, but at low resolution. And this is, again, resolutions of just 2,500 or so. And it is absolutely amazing what they've been able to get out of the data. So when they did that, they could see that each one of these populations, how they differ from, say, this base population here. You can see that there's, sodium and oxygen are varying in lockstep as a function of their population. But there's evidence that there's, in other elements, that there's discrete steps. There's a big step in aluminum as you go from one population to the next. That is not as continuous as in some of the other elements. And so this is hopefully going to open up a door. This is in the future. This is the only cluster it's been really applied to so far. But I have high hopes that this group will provide some really nice clues in the coming years on this. But just to say is that we took this idea because while we found multiple populations in terms of nitrogen spreads, one of the feedback that we got from the community is that nitrogen is an element that could be maybe coming from something else. So maybe we're not dealing with the same multiple populations. Again, it's coming back to the idea that maybe globular clusters are really different. And if that's true, then all of the constraints I told you about young massive clusters and the age constraints from 1978 then wouldn't mean all that much. And so in order to prove that, what we needed to do was look for sodium variations also in these young clusters. So that's what was done by Silvia Martocchia and Sarah Saracino this year. They studied a few clusters with MUSE. They used the same methodology by selecting stars in HST color magnitude diagrams, and then studied their differences in sodium. And that's what's shown here. The data is shown as a black line. The colored lines are different models of different sodium variations. We can actually measure the sodium differences within these two clusters. And we see is that by high significance, we see sodium variations within the clusters. So we see is that sodium within this young and intermediate age clusters, we see that sodium is also varying in the same way that nitrogens vary. So we can say that in fact, the multiple populations within these clusters is really the same as that seen in ancient globular clusters. William Chantereau did a similar study based on the horizontal branch in these clusters, found that the helium was also varying in the same way that we see in the ancient globular clusters. And therefore, I think now really comfortably say that young and intermediate clusters truly are just young globular clusters. Is that last bit of thread that said that maybe the cell populations are different, I think we can rule that out now. In fact, they're the same. And that gives us confidence of all these other studies that we've been doing, and hopefully you've been hearing a lot in Heidelberg, of using globular clusters to trace the assembly of galaxies, is that this just gives more credence to those types of studies because cluster formation is independent of redshift. So takeaway messages, globular clusters host multiple populations. They're not the simple stellar populations we always thought that they were. We see them in their strange CMDs, which is caused by unique chemistry within them. I didn't get a chance to talk about that, but there's really exciting tentative evidence that it may not be limited to globular clusters after all. We see stars that have hints of this strange chemical anomalies in the galactic bulge and also massive early type galaxies in the central regions. But I think those studies are still in their early phases. So we'll see what comes out in that in the next few years. Globular clusters are still forming today, known as young massive clusters. They share common stellar populations, so the multiple populations phenomenon is not limited to the ancient globular clusters. It actually is a common thread amongst all massive clusters. We don't see any evidence for age spreads or multiple bursts in young clusters, either through resolved photometry or integrated spectroscopy. And therefore, we can use young massive clusters to really test models for globular cluster formation and their multiple populations much more stringently than was ever possible before. And when we do that, all of the popular scenarios including my own, I should put forward. I didn't talk to you because I'm not going to advocate it, but I put forward my own scenario back in 2013, and the data that we've gotten in subsequent years also shows that that scenario is not right. So we have to move on. Over the last few years, we've been doing an HST survey, and what we found is that we found in all massive clusters greater than about 2 gig years, shows multiple populations. There is a strong influence of age and also cluster mass of what that controls the multiple population properties. But so that leaves us to kind of where I go back to the beginning, is that new ideas are needed. Is this due to something of cluster formation? Is it ISM physics of how clusters actually form? Is there something that we haven't understood about stellar evolution within these massive clusters linked to stellar rotation? Or is it a totally different direction? And hopefully somebody in the audience today will be the one to solve this problem. And then just to leave you, I thought one of my favorite diagrams that I put forward with Carmela Lardo in the annual review is for the main, at least in 2018, what were the main 4 scenarios for the origin of multiple populations? They're the AGB scenario, the fast rotating massive scenario, star scenario, the very massive star scenario, meaning the 10,000 solar mass scenario, and my scenario, the early disk accretion. And then we went through the literature and we found all the different constraints we can get from various aspects. So whether or not you can look at young properties of young massive clusters, or detailed abundance trends, or the fact that every cluster is individual. You can actually use this as a fingerprint, or the mass budget problem. And in X is where the observations were in direct conflict with the predictions of the model. And of course, these were not real in the sense we already had these constraints. So they were made in order to match those constraints. And where the other models were not doing very well. But of course, we could go on for this for a long time. In fact, there are many other constraints that we've been putting in this. You do helium spreads and how it actually goes as a function of cluster mass. The trends with the enriched fractions, lack of trends with metallicity, lack of trends with age, or the observed age trends, that none of the models have been put forward are actually doing particularly well when a critical eye is put comparing them with observations from independent groups. And with that happy note, I'll end.
Thank you very much, Nate, for a very didactic and fascinating talk. I will open the floor for questions. So please, if you have a question, raise your hand. I see Andreas Koch has already raised his hand. Please go ahead.
Hi, Nate. Good to see you.
Hello.
So until recently, there was this metallicity flaw, no globular cluster known below -2.5 or so. And now people are pushing that towards the -3 with new discoveries. And also some primitive systems like these ultrafaints show some globular clusters, or some star clusters, I should say.
Mm-hmm.
So I was wondering what your opinion is on this metallicity dependence. If one day we find a -4 cluster, would you also expect some of those multiple populations or abundance variations in those?
Yeah, so it's a very exciting time for that. There's been a lot of studies that have shown in massive galaxies that you get very few or no clusters below FE/H of -2.5 or so, as you say. And then recently there was one hiding in plain sight at -2.9. Now, was that an anomaly, or are we going to find more of those? I think that's a big open question. But what I've seen is that when we look at these very metal poor clusters, or used to be very metal poor, these -2.5 clusters, is that they didn't really show multiple populations that were radically different from the ones at solar metallicity. They were still showing sodium oxygen abundance trends. There was no really strong dependence on metallicity in the type of multiple populations we found. So my guess is that when we go to this M31 cluster, it's going to, with ELT, I think we'll be able to resolve it and actually get detailed abundances of individual stars. I'd be surprised if we find anything too different. So until I see bigger samples, I'm going to maintain that this was an oddball that was just part of the stochastic fluctuations of early galaxies. But we'll see. I think the jury's still out on that. But I'd be very surprised if we see any radical differences in the multiple populations.
Thank you.
I didn't have time to talk about this, but again, in 2016, one of the big pushes at the conference was looking at some bulge globular clusters, Milky Way ones, at solar metallicity. And basically the AGB scenario predicted that they shouldn't exist. You shouldn't see multiple populations there. But when it was looked, they showed all the same abundance trends. There's no really standard differences for me, although there might be some small trends, but we'll see with in the coming years with if those are maintained or not.
So while I wait for the next hand, I have a question myself. So you showed the main sequence for NGC 416, where you need to go down and maybe see a main sequence spread, given that it's just below the age threshold that you.
Yes.
So a question I have is it really necessary that you would get this main sequence spread below, indeed, say, well, you know, one solar mass, 1.5 solar masses or so? Because I could envision that indeed, if it's something related to crazy stellar evolution, it could kick in during the giant phase, right? And then you wouldn't see it on the main sequence.
So the say is that we do see it on the main sequence in the ancient globular clusters.
Right.
And so that was one of the first ideas back in the 80s, was that it was just a stellar evolution phenomenon with standard stellar evolution. But that doesn't seem to be the case, because we see this in unevolved stars. So HST has been amazing with this. They can go down to 0.2 or 0.3 solar masses, and you see the main sequence really splitting. So you see that the oxygen spreads, at least, all the way down the main sequence in unevolved stars. So that's why I would expect to see them here, although you could imagine some reason that age is the actual critical thing, that it's only after some time. But what that would be, I don't know.
That would be awkward on the main sequence if the stars themselves don't really evolve.
Yes, that's right. But the one thing that is changing on a low mass main sequence star that is changing as they evolve is that the rotation rate is changing. Is that there's pretty clear evidence now that a large fraction of them, at least in clusters, are born rapidly rotating, so possibly near breakup speed, and that over the subsequent gig year or so is that they're then break to basically have little or no rotation, similar to the sun. So again, I like this idea. I'm a big fan of stellar rotation being the cause of every solution in astrophysics, but to highlight, there's no reason a priori to think that that would cause any abundance trends. I've been trying to push people to do that, and there's no reason to think it. So, you know, it's just an empirical idea that I've been following.
And another sort of devil's advocate related question is, if you look at the age mass diagram of the clusters that you've looked at, then some people in favor of more classical models might say, well, those masses are actually relatively low if you assume that globular clusters were a factor of 10 to 100 more massive when they were born. You're actually not necessarily probing into the regime where we would expect or predict those to sit.
It's possible. There's two arguments against that, is that these clusters up here in this region which are different technique. So, you know, I think your point still stands, but is that we're finding with a different technique, we're getting the same story being told to us. And that between the ancient globular clusters and these guys, there's just a couple of gig years of evolution that we would not expect significant mass loss. And we see globular clusters today with masses down to 10 to the 4 solar masses that show it. So I think it's potentially true what you're saying, is that you could imagine some really evil coincidences that all go in the same direction that might fool us. But I could say, put my observer hat on and say this is the best we can do, because there's no more massive clusters in the Magellanic Clouds that we can look at with this age range. So this is until we can go to these kind of methods. But I think that's, you know, in terms of mass loss expected in these, I don't think that's true. And just to say is that we have other constraints on the mass loss of clusters, and this factor of 10 to 100 has been ruled out by independent means. But I agree, I'd love to have a consistent story itself, not have to go for outside evidence, but that's the best I can do at present.
Okay, thank you. So are there any further questions at this point? I have more questions myself, but I want to give other people the opportunity to ask a question. So Richard, please. Yeah.
Yes, can you hear me?
Yes.
I may have missed this, but you talked about the helium abundances due to the surface temperatures. My question is this spread in helium abundances asymmetric compared to primordial abundance of helium, or compared to H, whether you actually get a measurement at all at HE over H, and whether this is biased in one direction or the other?
So you were a bit quiet, but so just to repeat your question, tell me if I got it right, is that the helium abundances that we observe on the main sequence, the effective temperature, which is say shown here, is this measurement biased?
Compared to, is the result of the measurement going in direction of more helium compared to hydrogen, compared to primordial abundances, whether that's equally spread about the primordial abundance, or whether it goes in one particular direction?
Yes, so it goes in one particular direction. And so what you see is the nominal main sequence is well fit by, say, primordial helium. But now whether or not that is how the models are constructed, and we're actually looking at a delta, I don't know. But you see the spread always goes in this direction, and these over here are binaries. Now, helium is very difficult to measure, and this is indirect, right? Because it's just an effective temperature. And so it has been looked at in spectroscopic in a very narrow window of horizontal branch stars, where the temperature is just right, where you can actually measure this in chromospheric lines. It's not even a photometric line, it's a chromospheric lines. And when you do that, you get a consistent answer. The caveat that I would give is that that's been done for one cluster, effectively, 2808. And so, there's a lot of room that can be done there. Apparently, CryRes Plus, or CryRes 2, I can't remember the name, is coming on the VLT that they've been talking about. This is something that it should be able to do for a huge cluster they're excited about, and it's just been delayed. And then the other constraint that people have tried to put on this, but again, it's indirect, is that you can do the helium spread based on the main sequence and optical colors, and then you can do the helium spread based on the horizontal branch morphology, assuming you are modeling the horizontal branch correct, which is a difficult thing. But for people like Franca de Antona and Maritza Solaris, they are confident enough that they can do it, if they also get consistent answers amongst the helium spread. And so, for example, in this case, 2808, they get a helium spread of 0.15 based on the main sequence and on the horizontal branch. And I guess it's been done for 2 clusters now. Omega Sen's the other one, where they also have spectroscopic data directly on this. And so it ties together, but it's not nearly as solid as one would have liked.
All right, so basically, when you get on that diagram, when you get bluer, sorry, you're getting redder with P minus I, so you've got more helium.
Helium goes to the left, right? So you get bluer, so the stars get hotter the more helium you have.
Oh, okay. Okay.
And there's a couple, it's actually pretty remarkable. It's actually just a couple hundred Kelvin. And I think this goes to the amazingness of ACS, the precision that you get to see this is really phenomenal.
So you get less helium going to the left on that diagram.
More helium to the left, sorry.
Okay, that's what I wanted to hear.
Sorry, sorry about this.
It's going to feedback things. Helium doesn't form molecules. Hydrogen does.
Yeah.
So I was just, speculating in my mind, listening through, whether that would be in the right way you expect a stellar feedback type.
Yes. So you get less line blanketing effectively, so stars are warmer.
Yeah, well, H2 and HE also. Okay, thank you very much indeed. I think.
Sorry, I misunderstood your question. I'm sorry.
I have to do something about my laptop here. Thank you very much.
Thank you very much. Dominica, next question.
Yes, hello, thank you. for this talk. So this is not my field, so I'm maybe a little bit naive or unbiased, I guess, either way. My question is, with MUSE, I guess you can now also measure velocities, kinematics of individual stars in globular clusters. Do you expect that kinematic signatures may give you a hint to distinguish between different scenarios, maybe to come up with a new one? And whether you've also seen spatial variations between the different populations that you see in globular clusters?
Yeah, excellent question. So not naive at all. That is a major topic of study. And so people like Vincent Henault-Bruno and Mark Helios have been looking to generate models, actually Kenji Becky as well in Australia, basically to say, if I have HB scenario or if I have the early discretion scenario, what type of velocity differences might I expect between them? And the the answer is yes, you would expect differences. And amusingly, the two clusters that have been studied so far come to the opposite conclusion of each other. So one supported that they formed in a rotating stellar system, and the other not. And so in each of the scenarios, they kind of predicted whether or not rotation would be there in the kind of the subpopulation. And so the jury's still out. Now, one of the problems that we face is that for the ancient globular clusters, that these systems are dynamically relaxed, especially in the inner regions. So all of their initial kinematic substructure in the inner regions has been erased. And so that has what's been holding us back on the globular cluster. So there are people, Holger Baumgart and Ivan Cabrera-Zira, working in Australia, trying to do this exact same thing with large samples going well out, starting in the center of the cluster and also going to the outskirts, just seeing if they can look for these kinematic imprints on. And so, yeah, there's definitely hope that that's going to lead to some insight. The one kind of cool result that's been shown by the HST proper motion group was that there is pretty clear evidence of radial anisotropies, meaning that the strange stars did start more centrally concentrated and they're diffusing outwards. And so I think there's pretty clear evidence of that in a handful of clusters that has been measured so far. So that's definitely very promising, but so far no really strong results on limiting that.
Thank you.
Thank you. So yeah, before I see we're nearly out of time, but before we conclude, I would like to ask one more question, which I think is interesting in the context of what you've been saying, Nate, is that we need new ideas and new people working on this problem. So there is going to be a lot of new theories in the next couple of years. You mentioned ELT, but also James Webb, of course, is coming, hopefully. So where do you expect the most? And can you share some thoughts on what types of experiments you think would be useful, and which direction we could see developments with these new facilities?
Yeah, it's a good question. So I think the easy answer is James Webb. And it's going to be looking at the main sequence in these Magellanic Cloud clusters to really nail that down. So that's going to be the first thing that I would spend my time doing. But it's also going to be interesting in the galactic globular clusters to kind of go into the brown dwarf regime, to see if it continues all the way down to the substellar regime. Similarly, looking at high redshift, it's kind of a new thing that's opened up, looking at gravitational lens systems, where you actually can see globular clusters forming at redshift 3, say. And while I have just told you for an hour that it's the same that's happening in the antennae, of course, it's nicer when you actually have that image of redshift 3, and you can actually get a resolved spectrum of that cluster to show it also doesn't have multiple epochs of star formation in it. I think that's good. And so that's the kind of low-hanging fruit, so the first ones that I would be expecting. I think dynamics is a good one. So I think that the last question we had, I think that's an exciting field, and I know more and more modelers are going and getting into that to do that, and say trying to kind of, without pre-adopting models, to see what kind of differences you might expect. So yeah, those are the ideas off the top of my head where I think we can be pushing. Do you have any ideas on that? I know you've thought about this problem a little bit.
You know, I agree, especially on the high redshift one. I think it's one thing to get cluster formation right in the local universe and get the end product right in the local universe. But if you really want to combine everything, you should include the formation in the early universe that eventually led to those old systems we see today. So
I guess one thing I'd add that I didn't have a chance to talk about that I'm really excited about is integrated light studies of early type galaxies. Because as I mentioned, and I'm sorry I don't have time to discuss it, but there's pretty tantalizing early evidence that the same chemical abundance anomalies are in these early type galaxies, in these massive, in the centers, from the UV upturns to nitrogen and sodium enhancements. And so if they're tied, I think that could, one, open up the field hugely in terms of the importance of the problem. And also it tells us it's not globular cluster unique, but some kind of density maybe, as the inner regions of early type galaxies, the stellar densities overlap with that of globular clusters. Maybe that's somehow related, I'm not sure. And as I mentioned, there's a bunch of stars, 10% or more in the inner bulge of the Milky Way that seem to share this chemical abundances. And I know they got a bunch of recent time, Riccardo Schiavone and collaborators, to really nail this, the same abundance trends. Again, sodium, oxygen, where up till now it's really just been nitrogen that they've nailed this on. So expanding the problem to different areas, different types of galaxies, I think will be really exciting, and maybe to show that globular clusters were just the tip of the iceberg, in fact, of the types of stars that show this anomaly.
Okay. Thank you. Thank you very much. So before we thank our speaker again today, I would like to make two short logistical announcements. First is, if you have any further questions, of course, Nate, normally we would have loved to have you over in person. Due to the current circumstances, that's not possible. But if anybody here has further questions to Nate or would like to have a follow-up conversation with him, Nate has kindly agreed to do that. And so if you do, please send me an email or send Nate an email, or both of us, and we will arrange that. Then secondly, I'll steal the screen sharing here for a moment to announce next week's speaker, who's going to be our recent arrival here in Heidelberg, Saskia Hecker, who is going to be talking about red giant stars inside out and giving us insights into the magic of astroseismology. With that, we've reached the conclusion of today's joint colloquium. So please all, can I ask you to unmute and thank Nate once again for a fantastic talk.